Okay, so we're going to start looking at our very last module, which is module 7, mechanism design. Now, as we look at the learning plan here, you're going to notice that we're going to jump back to chapter 5 in our book. Okay, and I do have a PowerPoint presentation that we're going to be using to guide us through the chapter. There are a couple of the sections or some of the sections that we don't go over. I kind of focus on the things that are most important in here. So our PowerPoint will kind of help us with that. Additionally, we're going to have some example problems that we'll do that'll mimic the homework that you're going to be assigned, and then you'll be kind of ready to rock and roll with that. And then you're going to have assignment number 7 that is going to then reflect on the items that we're going to be going over. So we'll look at assignment 7 a little bit later. We'll start with the PowerPoint presentation and what we have underneath in chapter 5. I am going to, in the background here, I do need to open up my document camera so that I can reference it when we need to. All right. Here and back over here. All right. Mechanism design, chapter 5. So we've all looked at and we've seen 4-bar mechanisms up to this point. So the two kind of main categories of 4-bar mechanisms are going to be kind of that oscillating or rocker type, crank rocker as we refer to them, or as a crank slider. And all that means is that the crank or the input goes around a complete revolution, while the output, in this case, a slider, is going to go back and forth linearly. Or if we're in a crank rocker situation, the input link or the crank, the driver, is then going to go around in a complete revolution while the other one is going to oscillate. Okay, so let's take 1 minute to list as many applications of a 4-bar and a slider crank mechanism that you can think of. Okay, so get out a piece of paper and take 1 minute. I'm going to time you 1 minute for 4-bar and slider crank mechanism applications, like in real life where they would be. That's fine. That's fine. Okay, so that's a minute. Let's go to our next slide here. And I want you to take 1 more minute. I want you to do a quick Google search of more applications of 4-bar mechanisms and slider crank mechanisms to add to your list. So whether that's on the computer or on your phone, 1 more minute, let's kind of expand our list and find more applications. All right. So I'm gonna go to our next one. I'd like you to share one that you don't think anybody else thought of, okay? And we'll do kind of a quick, we call it a whip around on some unique applications. So I'm gonna start in the room here. Dylan, what's one application that you either thought of or you found that you don't think anybody else thought of?
Like a sander.
A sander. A sander. Okay. What kind of a sander?
So you would have, so obviously the slider crank's gonna drive the sanding, but you're gonna have like a sanding block on it.
Okay.
And that's would be what's gonna be sliding. Well, technically you have friction, but you're gonna have a motor driving that.
What type of a mechanism? Would it be a like a crank crank rocker, or would it be a crank slider?
You get a crank slider.
Okay.
Yeah,
All right. Or slider crank.
correct, yeah.
All right. Okay. So a sander slider crank mechanism. Okay. All right. Mitchell, what were you thinking? What's something unique you think you came up with or came across? What was that? Arm assemblies for payloader buckets. Okay. Good. Jacob.
Well, I guess like a recip saw.
Oh, a reciprocating saw. Yes, absolutely. All right. And that would be like a crank slider then, right? Awesome. Okay. Those who are online, who do I have online? I've got Alan. Could you share one with us, whether it's putting it into the chat box or verbally? It's up to you.
Can you hear me all right?
We can.
All right. What about I'm trying to think of the word.
That's okay.
Like a backhoe, like for the bucket.
Absolutely. Yep. Actually, we saw that, didn't we do that manual one kind of in a playground setting where it was like that scooper, right? Which
Right.
mimics that. Yeah. Jason, how about you? Feel free to put it in the chat if that's better. Okay. Mobility access chairs for swimming pools, heavy equipment, absolutely. Bus doors, yeah. Automated sliding doors, excellent. Your Google finds were pedal bikes and combustion engines. Awesome. Excellent. Yep. Great job. I found a pump jack as a 4-bar. It pumps oil out of the, oh, nice. Excellent. And then Eric, I think you're on. Oh,
Yep,
I'm
I'm
sorry.
on.
Eric did yours. Okay, I'm sorry. I thought I had, okay, Jason. Oh, Eric, you did yours. Sorry. Eric was the first one. My examples and the Google finds, and then Jason did the pump jack. Awesome. So really you have to think in terms of, so many times there are different, designs that we have that we want the motion to occur. And it's not always just a simple straight line motion. All right. Additionally, the work that we're going to end up doing out in industry isn't always going to be a tweak on something that's existing. So chapter 5 is about kind of the rules and how to approach problems that are unique and new so that you can design the mechanisms for the motion that you're looking for without having to have something already there. Okay. So as we look here, we made our list, we did that. As we look at mechanism design, we're going to learn how to use some graphical methods to initiate the design of mechanisms, find out why it's important to know these techniques and processes, and then also start to think about your capstone course and possible projects that you could work on. Okay. Where you're at in the program right now, you're kind of approaching, I think capstone is next semester, right? In the spring for you guys, right? So, so looking at and thinking about projects that you would want to work on, and then how the kinematic design that we've done here might play into that, whether it's, different types of drives, like whether it's gears, belts, chains, that type of a thing, or if it's going to be something completely unique and you need to, use other types of, whether it's a slider crank mechanism, or if it's a crank rocker, looking at, where do I start with that when I don't have something to actually go off of? And why is this important? Because for exactly that reason, sometimes we're not going to have an existing design. We might have a thought in our head, but it's kind of like that sketch on a napkin. We don't really have anything else to go from. So, so getting that started is what we're interested in here. So our objectives here in chapter 5 are to, number 1, describe mechanism synthesis. We'll do that early on. Design an inline slider crank mechanism. Know the desired mechanism time ratio, And then use timing charts to synchronize that motion, and then also use graphical methods to design various mechanisms, okay? And then the process involved in that. What's nice is we're going to find out that they do have a step-by-step process here for us to follow, which makes it nice. So in our first section here, 5.1, which starts at the very beginning of our chapter on page 109, synthesis, all right? So that's a little bit different word for us, but it's really just the process of designing a mechanism that produces a desired output motion for a given input motion. So many times we're going to know what our driver is, what our given is, like what do we have to start with? And a lot of times it's a motor of some sort or an engine. And then we have a desired output that we want to get to. So so it's kind of like figuring out that design process from what we have initially to where we want to end up with. Okay. Now, type synthesis is going to be selecting the mechanism that's capable of achieving the desired motion. So for instance, if I need oscillating motion, kind of like as a rocker, I'm not going to choose a slider crank for that. Okay. So understanding what the output motion is going to be relative to the input then starts to identify for us what's the type of mechanism that we're going to target for this application. Okay. And you know what? It sounds simple and it sounds easy, but trying to keep it simple is a very hard thing to do as a designer. Okay. The more parts that you have, the more complex it is, the more things can break. So if you can eliminate as many parts and keep it very simple, that is always going to be the goal of a designer. And again, that's not always an easy thing to do. And then dimensional synthesis is then figuring out what are the dimensions that we're going to be using? What are the actual lengths of the different links? And what's the space that this is going to actually take up? That's dimensional analysis. So, so we are going to be focusing mostly on that dimensional analysis because that's in the end where we're going to have to incorporate it into our designs. Time ratio. Symmetrical motion. Symmetrical motion is when we have an outward stroke, okay, is going to be identical to an inward stroke. All right. These are called kinematically balanced mechanisms. They're going to accomplish work in both directions. So as it goes around, it's going to have the same amount of time going in one direction as it does in the opposite, and just kind of go back and forth or oscillate, you know, about a certain angle. Engine mechanisms, windshield wipers, these are going to be symmetrical motion. Okay. Here's a video that we're going to look at for this type of a motion. I'm hoping in this, it will. Cool. So as you can see here, as this goes around, it has the same amount of time that it takes to go in its outward stroke as it does on the inward stroke. And if we would extend the center line, if you would, along from that driver through the center of our slider there, we're going to notice that those are in line. So this is an inline crank slider application. So timing wise, you can see that it's the same amount of time that goes forward and back. So I'm going to stop that one. And go back over here. Now, the next type of motion is non-symmetrical motion, okay? And this is going to be applications that require a difference in the average speed on the forward than on the returns. Most often on the returns, we're not going to be doing any work. And so it's going to be what we call a quick return. All right. So work is only going to be done on that forward stroke. The return is going to be as fast as possible. Okay. So cutting machines, saws are very much like that. Package moving devices are like that, where they're going to be moving in one direction, but then they've got to return and kind of go through that again. So in that case, let's look at our next application here. So you'll notice here, as it goes to the left, that slider goes to the left, that's going to be the slower side. And as it goes back to the right on the return stroke, it's going to be going faster. So again, because it's the return stroke where technically no work is going to be done, we're not really seeing exactly what this is intended for. We want to make that return stroke where the work isn't going to be done as fast as possible. Okay. Let's keep looking. Now, this is a little bit different mechanism than what we've seen, but it does offer that quick return in a non-symmetrical motion category. I don't know. I think that's long enough. You get the idea, right? So we'll stop that, go back over here. Now, some equations that we're going to be using as we do some of our design. And I want to go through and identify each one of these. The first one is time ratio. Okay. And this uses the variable of Q. This is on page 109 in the second column. This is equation 5-1. So if we go underneath, I'm going to zoom in here. The equations that I'm referring to are right at the bottom of that second column here. So equation 5-1. Q, the time ratio, is going to be the time of the slower stroke. Okay. So, so in the case of like what we saw earlier, that's going to be like where the work is going to be done. Okay. And then you're going to divide by the time of the quicker stroke. Okay. And that's going to be usually on that return. So these are different. So if we have a symmetrical motion and our Q is equal to 1, that means that the same amount of time to go in the outward stroke is going to be the same amount of time as the inward. So that's going to be symmetrical motion. But when we have a non-symmetrical or have that quick return type of an application, our quicker is going to be on the bottom here. So that means that this value is going to either be greater than or equal to 1. All right. Now the imbalance angle, beta. This relates to the geometry of a specific linkage and its timing to the stroke. Okay. So beta will either be something that we calculate for, or it's going to be something that is given and then we use it to determine our time ratio. And so you can see here, this relates the time ratio to that beta. And then also backwards, these three all stack together. If I want to know what my beta based on a time ratio is, this is rearranged in order to do that as well. Okay. Go back to now, I think we have to turn our page at the top of the next page. Then couple others. We've got our we've got change in time, and this is going to be the amount of time that we're going to perform a cycle, for instance, and it's going to be the time of the slower stroke plus the time of the quicker stroke. So that's going to be the entire time that we need to do that motion. All right. So the time of the cycle. And then once we know the time of the cycle, we then can calculate, all right, what is the crank angular velocity? Okay. So this is going to be, it says to the -1, but it's really the reciprocal. So it's taking 1 revolution and dividing it by the total amount of time that we need to do that motion. So let's take a little bit of time and we're going to look at example problem 5.1 here. Example problem 5.1. So I'm gonna underneath here. Gotta grab some paper and a pencil. And we'll do this one together. So I know that it's here, but as you know, it's always kind of nice to be able to walk through the example so that we get a little bit of experience with it. So I encourage you to take out some paper and we're gonna go through this problem. Get rid of this. Now, if we go back, I'm gonna catch us up on our PowerPoint. So it says here, we want to determine the time ratio, the imbalance angle, which is that beta, and the crank speed, which is W. So as we look at our example back underneath here, it says we have a quick return mechanism is to be desired where the outward time of the stroke is going to consume 1.2 seconds and the return stroke is going to be 0.8 seconds. We want to determine the time ratio. That's going to be our Q, okay? The imbalance angle, beta, our cycle time, which is change in T, and the speed, we'll call it W2 of the mechanism that's going to be driving, okay? I'm just going to check. Do they call it? Oh, they call it the crank. Yeah, the crank in our cases is a lot of times that I'll put crank here is going to be the angular velocity of link number 2, if you would. All right. So first things first, time ratio. So this is example 5.1, right? Example 5.1. So calculate the time ratio. So Q is going to be equal to, so if we go back to the previous page here, our equation for the time ratio is one of two equations here. If we know that imbalance angle or that beta, we can use this equation, but in this case, we do know the time of the strokes, okay? So we had a time of the outward stroke, if you would, and of the inward stroke. So we're going to use those. So as we line this up here, if we look at the outward stroke, that's going to be equal to what we call T1. That's the first part of the motion. And then the return stroke is going to be T2. That's going to be the second part of it. All right. So when we look at Q, we want to use the time of the slower on top divided by the time of the quicker on the bottom. So when we line up T1 and T2 here, T1 is 1.2, T2 is 0.8. So that means that our T1 is going to go on top and our T2 is going to go on the bottom, right? So filling in those numbers, T1 is 1.2 seconds divided by 0.8 seconds. Seconds cancel out here. It's just a ratio. And our Q then, what do you get for your number? 1.2 divided by 0.8. 1.5, yes. 1.5, okay? So that's the first part of what they were asking us to get, right? Now we want to know what our imbalance angle is. Let's go back, beta. On the previous page, you're going to notice that beta is calculated, beta is equal to, and we need our Q's here. Well, we just calculated our Q's. So we're going to use that equation to calculate our beta. So I'm going to call this step number 1, this step number 2. My beta is going to be equal to 180 degrees times Q minus 1 and Q divided by Q plus 1. Okay. So now using our Q from above here, that's going to equal 180 degrees times 1.5 minus 1 and 1.5 plus 1. Okay, so that goes right in there. So then our beta, make sure that you can do this. So even if you see the answer, oh, it doesn't look hard, make sure you're doing this along with us because it gives you that experience of plugging this into your calculator and making sure that you end up with the correct answer. So anybody get their beta yet, or let me know when you do. 36, yes, and it would be 36 degrees, right? Yep, because the degrees is here. These are dimensionless here. So 36 degrees, excellent. And if we compare to the book, they got the very same thing as well. Okay. All right, so we've got beta done. All right. The next thing we need to do is determine the change in T, or the cycle time. The cycle time is the total amount of time we need to in order to perform this measurement, or this this motion. So up
Hey,
here on
Kelly.
the top, I'm sorry, yeah.
I have like a Q equals 180 plus B and then 180 minus B. Did I just write that in the wrong spot? Or what is that equation for?
This one?
5.2.
No, for
This
like
one?
I was trying to read off my phone, so it was like yeah, that one.
Well,
Oh, that's to figure out Q a second way.
Yes, exactly. That's to figure out Q if you know what your beta
Okay.
is. Sometimes that's given.
Okay.
And then
Um,
this one down here to solve for beta is just a rearrangement of.
Okay, and that's the imbalance angle.
Correct. Yep.
Okay. Thank you.
You're welcome. You're welcome. All right, so moving on to the cycle time. So the cycle time is the amount of time we need to perform the motion. And in this problem, the two motions that we have are the 1.2 on the output and the 0.8 seconds on the, I'm sorry, the outward, and then the 0.8 seconds on the inward or the return. So the total cycle time is adding those two together. So step number 3 here then is going to be change in T is equal to T1 plus T2. So we have 1.2 seconds plus 0.8 seconds. So our change in T, or our total cycle time, is going to be adding those two together, which is 2 seconds. Okay. All right, and then, so we've got that done. The last thing we need to do is determine what the speed of the mechanism that's going to be doing the driving. So that's going to be the angular velocity of our crank, our W of our crank. And that's right here. Okay. So it's equation 5.5. So if I go to number 4 here, my W of my crank, it's going to be equal to, now I'm not crazy about the way that they write that out, but I think a more clear way to write this out is that we leave 1 revolution on top, because our motion is 1 revolution of our crank in order to do the motion, or the 1 cycle that we desire. So divided by the change in time. So if the change in time then is the 2 seconds, that goes underneath here. The way that they write it out is change in time to the -1. So I think it's just, it's not wrong, but it's a little, I think it's a little incomplete. Okay, so I encourage you to write it out like this. This is the very same thing, and 1 revolution goes on top. So we're going to then say, okay, 1 revolution on top divided by 2 seconds. Okay, so our W of our crank is going to be equal to 1 divided by 2. You should get 0.5, right? Well, let's look. Yep. So revolutions per second, right? 0.5 revolutions per second. Now, as we know, that really isn't, those aren't the units that we're, going to be used most often. So what do we want to change it to? RPMs. Yes, we want to change it to RPM. And so we simply do a conversion where we say that 60 seconds is equal to 1 minute, right? Seconds cancel. So this is also equal to 30 RPMs is equal to W2. Okay, so if you're looking for the angular velocity of your crank, your W of your crank, you'll get it first in per second, but then convert it to RPMs, or revolutions per minute, for your final answer. Okay.
Now, is this one of those where you have to continue to use the original W? Because like the last time we did, if you had, it was for, you had to keep it in rev second, continue the rest of the problem.
It'll just depend on what you have. You'll figure it out, right? Depends on what you have coming up. So if they give you revolutions per minute in a problem, but then you need to get back to, for instance, what are the seconds here? Then you might have to convert in the opposite direction. So yeah, always put your units in because that'll also be your guide on what you need, okay? All right, other questions? I think that completes what we needed for this one, right? Yeah, 30 revolutions per second. Cool. All right, any questions so far? It's kind of fun. Kind of fun. All right. So the next section we're going to look at is 5.4, which is the design of a slider crank mechanism. So we're skipping over a couple things here, and we're gonna jump to slider crank mechanisms. So a slider crank mechanism is going to provide reciprocating linear sliding motion for a component. We've seen this many times. We've looked at them. Let's just take a peek at a quick YouTube video. This is going to be the application for an engine. So you'll notice here that the piston is going to go up and down within the cylinder, and it goes around the crank, and it changes that rotational motion. The crank is your input to linear motion here. Okay. All right. So it's going to kind of get rid of some of these so I don't have too many open. The other one that we see here are some other applications. I know engines are kind of a, kind of a standard, but a sewing machine, hacksaw, a compressor. I forget which one this one is. Oh, this is a hacksaw one. Sorry, we've got an ad we have to listen to for a second. There we go. I guess. I think, Jacob, did you mention a hacksaw or a reciprocating saw? Kind of like similar. Sure. Probably, yeah, depending. I would think, yeah, yeah. There we go. There you have it. So it's kind of nice sometimes to see those in motion. I know we looked at a lot this semester in just plain diagrams, and I know you can visualize a lot that way, but it's kind of nice to see them in their kind of simplistic mode, if you would. So as we kind of continue on here, inline slider crank mechanism, if we look at figure 5.3 on the top of page 114, we're going to look at the stroke. Now we've identified stroke when we looked at slider crank mechanisms and doing the kinematic diagrams and such, and especially in the analysis of its displacement. But as a review, the stroke is going to be the furthest out position that our slider is going to have compared to its closest position that it's going to have. Okay, so if we're rotating around, this would be our outbound and this would be our return. And the difference between those two positions is called the stroke. Okay, stroke. I'm not sure why, but the book takes, and we saw this as well when we were looking at displacement analysis. I think that was chapter 3 or 4, I forget. And it does delta R instead of like a distance. Okay, but delta R is going to be the overall stroke, and that max value from the furthest away to the closest. Okay. Now, as we look at an inline crank slider mechanism, okay, our L2 is going to be the length of our first link off of the frame, right? The length of link number 2. That's our crank. So how long is that crank going to be? Well, when this is in line, this is going to be laying down flat, right? And that's going to be its furthest out position. And then when this is on the exact opposite side, this is going to be the closest. So do you see how the stroke is the same between these two? Okay, so that means that our L2 is going to be half the amount of the desired stroke. So if you know your stroke to be, I want it to be 16 inches, my L2 has to be 8. Has to be 8, because when it's on this side, it's going to be 8 inches. But when I pull it all the way back, now it's going to be 16 back. So it's going to be the 8 on the other side. Okay. So L2 is going to be equal to our stroke. Okay. Remember, this is stroke divided by 2. Stroke divided by 2. All right. Now, on an inline slider crank mechanism, that forward stroke is going to be identical in timing as the return stroke. So you can actually do work in both directions. All right. You don't have to, try to go back faster. So a quick return assumes there's no work done on that return. So it tries to minimize the amount of time that we're going to take to do it, where it slows down the work cycle, the work side of the things. This is also called symmetrical or balanced motion, right? Now, continuing on, determine the appropriate lengths. As we said earlier, the L2 is going to be half of whatever the stroke is, or we can say that the stroke is going to be 2 times whatever the length of that crank mechanism is. All right, that's equation 5-8. Now, as we look at the connecting rod, the next link number 3. So connecting rod wise, when we talk about connecting rod, our slider is going to be link number 4. Our connecting rod is going to connect the crank to the slider. So this is link number 3. So the length of link number 3 is kind of that next rule that we have here. So a rule of thumb is that connecting rod is going to be 3 times or more whatever that crank was. All right. So it doesn't affect the stroke at all. It doesn't affect the stroke at all. It only is going to affect the amount of acceleration that we have. So the shorter that link is, the more acceleration there is. All right. So we want to minimize that. And I know if you would continue on and you would go to, for instance, a dynamics class, now we're going to be figuring out what inertial forces are. And inertial forces are forces that when we have something set in motion, we got to stop those. Okay. So if we have high accelerations and we have a lot of mass, that can be a problem. Okay. We want to try to minimize that. So to minimize that, when we're looking at a slider crank mechanism, is to make that connecting rod longer. All right. Rather than shorter. So rule of thumb, first and foremost, is to make it 3 times longer than what your crank is determined to be, which is half of the stroke. And then what you're going to do is you're going to then go from there, depending on the spatial relationship that you have. Okay. Let's look at an offset slider crank mechanism. Now, an offset slider crank mechanism, we have a new length. It's going to be L1. L1 length is going to be referred to as what we call the offset length. And that's going to be the offset between where the driver's center is and where the center of that slider is. Okay, so we've seen offsets. So if we go to figure 5, I think it's figure 5.5, not figure 5.35. I think it's 5.5. I think the 3 was the last one, and then I added 5. I didn't delete it. So this is an offset slider crank mechanism. So the offset comes in this L1. So here is the center of rotation for our crank. And down here is going to be the center for the travel of that slider. All right. So we have an offset here. We have an L1 between those two. All right. Now that length of that offset is going to have to be within a range, okay, that we see here. So it has to be less than, if we take the length of link number 3, which is going to be our connecting rod, minus the length of the crank. So L3 is connecting rod, and L2 is the crank. And then L1 is our offset, okay? And you can look right over here to the top of the next page. Here's our L3, here's our L2, our crank, and here is the offset L1. So L1 is not on the mechanism, okay? It's the distance between the center of rotation of our crank and that linear travel of our slider. All right. Now, when we have an offset slider crank, this is a quick return situation. So we're no longer have the same amount of time in one direction as we do in the other. We're going to have a shorter return stroke because of that offset. All right. So if that's something that you desire in your motion, then now you're considering this type of a mechanism as opposed to an inline. Okay. Also, when you determine those lengths, your stroke is going to be greater than 2 times the length of L2 or that crank. All right. And the range of that offset has to be in that range that we said. It has to be less than the L3 length minus L2. L3 minus L2. Now, additionally, if we look at, it's kind of made things bigger when I made it a PDF, it looks like. If we go back underneath here and we look at the offsets that we have here, you'll notice that they're giving us, you know, some ideas of how we're going to lay this out. So when we have our extreme position, for instance, this distance from the center is going to be equal to L3 plus L2 all the way out. And that's going to be as far as that's going to go out. So you know along that line where that's going to be. Then the closest position is going to be L3 minus L2 when they're like overlapping. So we've seen extreme positions before, and along its line of action, that's where this closest one is going to be. So the difference between these two, again, is that stroke. Okay. Now, the procedure for designing a slider crank mechanism. Now, this procedure is really the same for both, whether it's an inline or it's an offset. It's just that we don't worry about offset if we're an inline. So you're going to locate the axis of the pin joint on the slider. Then you're going to draw the extreme positions of the sliding link to mark off the desired stroke. So again, if this is offset, you then going to include that offset distance. If this is an inline, then it's going to be in line with that center of rotation. Okay. Then for an offset link, this is the equation that we're going to be using for the length of link number 2. It's going to be half of AC2 minus AC1. So we're going to go back to underneath, referring to this diagram. Here's here's C1 and here's point A. So AC1 is the length of this line right here, which is L3 minus L2. See that? And then the length of AC2 is from here to here, which is going to be L3 plus L2. And they refer to each of those, you know, in each one of these equations. When we do our example for this, illustrating this process, it'll make more sense. But here is kind of the main highlights, if you would. And then lastly, then you're going to complete the diagrams. And that's going to be something that I'll be showing you through an example problem after we're kind of done with lecture here. Mechanisms that produce the longest connecting rods are going to have those lower accelerations. So even for the offset slider crank here, that's true. And we're going to have lower inertial forces. Again, inertial forces are going to be that combination of the mass that we have that we're moving multiplied by the acceleration. So the higher the acceleration, the more those inertial forces are. And I'm not saying that inertial forces are bad. They're inevitable. We have to deal with them, but we do want to minimize them because if they get really large, they're just harder to stop and to get going. Okay. So rule of thumb again, the connecting rod number 3, L3, is going to be 3 times whatever the crank is determined to be. Now, the last type of mechanism that we're going to look at designing is going to be the crank rocker mechanism. Okay, the crank rocker mechanism is going to be where we have the crank going around in a full circle, but then the output, the link number 4, is going to be oscillating back and forth. It's going to be or rocking. So let's look at our first illustration here of this.
Michael helps turn your ideas into I did it.
So here on the left-hand side, you can see that crank is going around a full revolution while our rocker, our link number 4 on the other side, is only oscillating back and forth. only oscillating back and forth. Okay. So pretty simple. The next one that we have here, a classic example of this type of a mechanism is going to be a windshield wiper. Now, this is a single windshield wiper mechanism, but you can see the crank is going around and that windshield wiper is doing the oscillating. It's only 20 seconds. It's short.
Ones that are opposite, they just have that, but one's getting one. So you have some now where they.
Well, there's a number of different ways you can do it, but a lot of times the crank is on the middle and then there's an arm going to each one that then goes back and forth.
I know Ford started doing one, but they have much of them that start this way.
Yep, could be. Mm-hmm. Yeah, so there's multiple different ways, but that's a kind of a classic example of that. Now, when we talk about a crank rocker, the output that we're looking at is called the throw angle, okay? And that's gonna be the angle for which we wanna do our total oscillation through, all right? So the throw angle is gonna be the angle between those extreme positions on that rocker link, okay? So if we go to page 116 and look at figure 5.6, we'll see a crank rocker mechanism here in its kinematic diagram phase. So at the beginning here, up on the top, we have our crank, all right? And then our rocker or the oscillator is going to be link number 4, okay? So in this case, we're gonna put our link directly vertical and then half of our oscillation or our throw is gonna be on either side. So the total angle between C1 and C2 is going to be that throw angle. So the throw angle, we call it throw because it's not a stroke, because it's not linear, but it is really kind of that same idea. It's the furthest out position that we're gonna oscillate or rock to, and then pivoting around a fixed center, we're gonna come back to the other side. So it's called the throw angle. You probably have heard that terminology before. Now, the crank rocker can also be used as a quick return mechanism, all right? And the radial length between the two extreme positions is going to be 2 times the crank length. So we'll see how that equates to that. And here is the process as well. Now, again, when I looked at when we went through the process of the last one, it's kind of hard to imagine it unless you actually do it. So we'll show this you know, kind of in its process form in just a bit when we look at some examples. Okay. Now, mechanisms that produce a longer coupler length, again, are going to keep those accelerations lower. So when we look at coupler length, it's always that coupler between our input, which is our crank, and our output, which is our link number 4. In this case, it's that oscillating link on or rocking link on the end. So that L3 in between, it's not going to affect anything. It's not going to affect the stroke. It's not going to affect the throw, but it will keep our accelerations lower. So you want to minimize that as much as possible while still meeting that it's 3 times whatever your crank is going to be. And then we'll talk about transmission angle as well. We want this to be anywhere from 45 to 135 degrees and kind of staying as close to 90 as possible. But again, this will make a little bit more sense when we do some problems. So the last couple slides here are looking at working some problems at the end of our chapter as our examples, if you would. In the book, they didn't have any examples to walk through this process. So what I did was I picked out at the end of our chapter some problems for us to work on so that we can, you know, mimic what I have assigned for you guys. So the first example problem we're going to look at is 511. And what it wants us to do here is to design a slider crank mechanism using the information found in the problem statement. So we'll look there. And they want us to specify the lengths of link number 2, which is going to be our crank, link number 3, which is the connecting rod, and the crank speed. So what is our W2 or our W of our crank? All right. So let's look at our problem statement. This is found on page 120. So I'm going to go underneath here. And at the top of the second page is where we're going to be looking. All right. So as we look at 511, it says for these problems, design a slider crank mechanism. Now they're giving a time ratio for each one. So Q is our time ratio. In this case, for number 11, it's going to be 1. The stroke, which is that delta 4, is going to be 2 inches. And the time per cycle, so that's going to be the time in seconds. Okay. It says use, and that's going to be for the full motion that we're going to be desiring. So use either the graphical or analytical methods. We're going to use graphical to specify the link lengths, L2, L3, and the offset distance, L1, if applicable, and then also our crank speed. So as we look at this problem, a piece of paper here, what we want to do is we want to write down what we have. Okay, what we have. So we're going to focus here on problem 511. Okay, so 511. Okay. And what they're giving us is Q is equal to 1. Delta R, which is equal to, I like to say that's our stroke. I just feel like delta R is just a weird variable to use for a distance, but they do. Our stroke is going to be 2 inches. Okay. And our time, now this is, they're just calling it T, but this is the time per cycle. So that is actually delta T, according to our equations, is equal to 1.2 seconds. Okay, 1.2 seconds. Now, what we need to find, right? I'm going to kind of draw a little line over here. So we need to specify the length of link number 2, link number 3, okay? Offset distance if it applies, okay? We'll see if it does. And then we also need to find out what is our W of our crank, or most often it's considered W2, right? All right. So where we're going to focus equation wise is going to be kind of at the beginning of our chapter. So if we go back to starting on page 109, we're going to be using the equations that are here, as well as the equations that are up here. All right. So let's see what we can do. So first of all, it's telling us that our time ratio is 1. Okay, our time ratio is 1. Now, if that's the case, and we go back and we look at our Q equation, that means that the time of the slower stroke divided by the time of the quicker stroke is equal to 1. So what does that tell us about each of those comparatively? It's probably an inline, right? An inline slider crank, but why are you assuming that, Mitchell? You're kind of going 2 steps ahead. Before you determine that, what is this telling us about these two? Yes. Yes, the return stroke is the same as the outward stroke, right? It has to be. If I'm going to get a result of 1, that's what it has to be. And then, Mitchell, this means that it's an inline application. So that means that our L1 is actually non-applicable. It's not going to be offset because this is going to be inline. Okay, this is going to be inline. All right. So now if I'm in an inline mode, so I can say that this is going to be an inline slider crank mechanism, right? Inline slider crank mechanism. Then if I turn the page and I go to a couple pages here, and I go to page 114, I know that the length of my crank, L2, is going to be half of what the total stroke is, right? I know that to be, because up here, because it's in line, it has to be half. So this is going to be its outward, this is going to be its inward. And so because it's rotating about that middle, my crank angle is going to be, or my crank length is going to be equal to half of whatever that stroke is. All right. So because of that, I can say then that L2 is going to be equal to my, I'm going to write stroke. I hate that. I hate delta R. Stroke divided by 2. And I know my stroke to be 2 inches. So my L2 is going to be equal to 1 inch, right? 1 inch. Make sense? All right.
Do you care what variable we use for stroke?
What do you mean?
'Cause you-
I don't. Either one of the two. Either use do delta R
Don't-
or stroke. Yeah, pick one. Well, and you know what? I kind of, again, I don't know why they use delta. Why would they use delta R? I don't get it. To me, D, stroke. I don't know. Like, let's keep it simple. Delta R. I know. I'll put inches there. All right. So we have our L2 done. So we know we have this one done. We know that it's going to be 1 inch. All right. Let's take a look. We can also do crank angle at this point, or I mean crank speed. Okay. So let's look at the equation for crank speed. Our crank speed is on the top of page 110. And that is going to be 1 revolution divided by the total cycle time. All right. So we know our total cycle time is 1.2 seconds. Okay. So all we need to do for W of the crank, and like I said earlier, a more complete way to write this out is 1 revolution divided by our change in T. All right. So that's going to be equal to 1 revolution divided by 1.2 seconds. Right. So we should get 0.833, and this is going to be revolutions per second. But because it's crank angle, we want to convert this to revolutions per minute. So we're going to say 60 seconds in 1 minute. Seconds cancel. So our crank angle, or I say crank angle, our crank speed is going to be 0.833 times 60. So this is going to be 50 RPMs. Okay. There, we've got that one figured out. So we've got that one done. Right. Now we need to determine just our L3. Okay, just our L3. Remember, L1 is not applicable because this is an inline, so there's not an offset distance. That's what L1 is. So L3 is going to be the last variable that we need to determine. So if you recall, for a slider crank mechanism, one of our rules of thumb was that, let's see if I can find where it is in the text. I know I have it on my PowerPoint. I think it's somewhere in the, in like a paragraph. I apologize. But I know it's 3 times to minimize the resulting acceleration. So I'm not finding it right now. I know I'll come upon it at some point, but we can determine our L3 is going to be 3 times our L2. Okay. And this is going to be minimum. All right. This is going to be, I'm going to say minimum. So you could make this longer if you wanted to, because remember that connecting rod has no bearing on the stroke itself. All right. So we can say 3 times 1 inch, because that's what we found L2 to be. So our L3, and I'm going to put minimum here, is going to be 3 inches. Okay. So you can always make it longer if you wanted to. And you just don't want to make it shorter. And the longer you make it, the less acceleration it'll have, the less inertia force is going to be induced. Okay. All right. So numbers wise, that's what we have, but we're not done, because graphically you need to lay this out and draw it out in a kinematic diagram form. Okay. So what we're going to do is I'm going to show you now. I'm not going to walk through the entire process, but I'm going to show you what you need to do in order to, I actually want to do an open. And this is problem 511. Okay. I want to show you what you're going to be like handing in, an example of what you would be handing in. All right. Okay. So let me go like this. All right. So here, what you're going to notice is I have my slider crank mechanism. I used my object lines to show, if you would, the you know, all the way laid out in the slider in its furthest out position. So it would be L2 plus L3 all the way out here. Okay. And then I use hidden lines to show then where I would be on the opposite side with my crank, but then my slider pulled in so that the difference between those two is 2 inches. Okay. So you'll notice that my slider, my length of number 3 is 3 inches. And I should have done this differently. The total length this is deceiving. I'm so sorry. I have this on here wrong. Let me put this on correctly. I want to cross the entire diameter. I apologize. I just want to be from here to here. That's 1 inch is going to be my L2. And that's the length of my crank on link number 2. Okay, so it's 1 inch. The total distance across would have been 2 inches. So it would have been that number. So questions on that? So I'm not going to walk through the entire process, but using those numbers that we just talked about, this would be a physical representation of. Now, also remembering that the minimum length of L3 is 3 inches in this case. Okay. You could make this 4 inches. You can make it 3.5. You can make it 6 inches. And all that you're going to do is you're going to effectively reduce the acceleration on that part. Now, we're not worried so much about inertial forces, but that is the end result of minimizing accelerations. Okay. So questions on problem 5-11. Okay. Then your counterpart for your assignment is going to be problem 512. Problem 512. So I'm going to actually go underneath here. So problem 11, what we just did, is going to be your guide, if you would, for completing problem 512. So notice that your Q is 1 again, so it's going to be a symmetrical motion. Your total stroke is going to be 8 millimeters, and your total time for 1 cycle is going to be 0.08 seconds. So notice here, this is a metric problem. So when you're laying this out in CAD and you're going to be, you know, creating the drawing, just make sure that however you draw it, that what dimensions you come out with, I have to be able to see them. So I mean, it's up to you how you want to do this, but you have to make sure that when you kind of futz around with your dimensions, that they're going to be readable. So if you have a template set up from a previous class where you've got the millimeters and then it has all of the dimensioning set up, or if not, then remember that AutoCAD defaults to inch increments for their dimensioning, then you just have to scale it to a factor of 25.4. Okay. So just to keep that in mind. Oops, I see that. We can't see online. Oh, I wonder why. Hold on. Okay. Let me stop sharing and then I'll reshare. I don't know if it hiccuped or what. Now you guys can see, hopefully. Yes, now you can see AutoCAD. Perfect. Thank you, Eric. Thank you. All right. So, so this would be the result of, you know, what you would want to be looking for, taking a screenshot, something similar to this. Okay. Any questions about that? All right. Then let's look at our next example problem. So the inline, I think, is the most straightforward. I'm gonna say maybe the easiest, but we don't want to leave it just at that. So the next one we're going to look at is problem 515. And here we're going to have a slider crank mechanism. We want to look at the information and design the lengths of each one of the links for this one. So let me get my 515. All right. Let's see, why does it do this? Okay, so 515, we're going to go down a little bit in that same section. So we're still in slider crank mechanism mode. but this time our Q is 1.37, okay? It's not 1. So that means right away, you know, this is going to be an offset slider crank mechanism. So we're going to now have to determine an L1. Here's our maximum stroke, 46 millimeters. And then we have our total time for our cycle is going to be 3.4 seconds, 3.4 seconds. So let's find a place where I've got it open. There we go. Okay. So let's write down first and foremost what we know about this example. All right. What do we know about this example? So for number 15, this is problem 515. Our Q is equal to 1.37, right? 1.37. Our delta R, which is also equal to our stroke, is equal to 46 millimeters. And our delta T, even though they call it T, they're giving us the cycle time. It's called delta T in the equations is equal to 3.4 seconds. Okay, total. All right. All right, so now what we need to find, okay, so we need to find same things as above. So as it says here, we want to graphically determine L2, L3, and then an offset distance if it's applicable. So L1, L2, and L3. We want to find all the lengths of our links, okay? And then we also want to know what is the W of that crank, okay? So as we look here, where do we want to start? Where do we want to start? Well, we're going to look at number 1, back at those equations. Now, maybe we should make an equation sheet. I'm wondering. It's nice to have them all in one spot. We know that our crank W, or the angular velocity of our crank, is going to be 1 revolution over the total cycle time. So we actually have the total cycle time. So we can go ahead and calculate W right away. So I'm gonna do that. I'm gonna say W of my crank is equal to 1 revolution divided by that total cycle time, which is the change in time. So 1 revolution divided by 3.4 seconds. So you should get 0.2941 revolutions per second, right? And then we're going to convert that to revolutions per minute. So we've got that one done. Now, the purpose of the Q is only to let us know that this is a quick return, okay? This is a quick return, and we may use it in a little bit, but yeah, so that's that. What do we want to do next? Number 2, probably start looking at some of these items here, right? Some of these items here. So for our offset, if we look at that section for the process, we know on page 114 in the offset crank mechanism to find that offset distance L1. Remember, the offset distance is this distance between the center of rotation of our crank and the distance that our slider is going to be, you know, on that travel. So it's this, in this case, vertical distance, okay, L1. Now L1 simply has to be less than L3 minus L2, okay, L3 minus L2. Now, if we look at equations for L2 and L3, this is where up on the top of page 115, here's our equation for L2, and these are referencing A as the center of rotation of our crank, and then the C1s and the C2s are the distances either to the outermost at the extreme position or the innermost extreme position, okay? So what it means is you have to first pick something to be your offset distance, okay? So I did draw this out. And I drew it out in AutoCAD, and this is number 15, right? File open. Now, again, I'm not going to start from scratch. I'm going to kind of show you how I went about this process, okay? Now, as we look here, the first thing that I did is I identified and I drew out my stroke. 46 inches is what we were given, okay? And I randomly did an offset distance of 10 millimeters. All right. I really didn't know. I just knew that it had to be less than whatever my difference was between my L3 and my L2. And I didn't really know what those were yet. Okay. So I wanted to just kind of lay this out so I knew where about my center of rotation would be. Okay. Then what I did is I picked a length of my connecting rod to be 75 millimeters. Okay. So when this is all laid out to my furthest out position, my radius to here is 75 millimeters. So now if my L3 is 75 millimeters, my crank is going to be 1/3 of that, right? 1/3 of that. So that's 75 divided by 3 is 25. Now remember, my stroke is always going to be greater than whatever my crank is. There's not a hard and fast relationship on an offset slider crank mechanism, okay? So once I have this set, okay, now I have then where things are going to be. So then I constructed along my 10 millimeter line, I did a radius here of 75, and then I did a radius of 25 here so that I could see exactly where my furthest out position would be. Okay, then, and I erased it because it got to be too many lines. I would do that very same thing here, but this time I would show that, let's see, not, oh, maybe I'll do hidden, that's fine. I would show that from this position through my center, because it has to go through the center. Center. There we go. And then I would extend to the outermost. So let me do my trim, extend. So extend, it's gonna have to go a couple places, extend, and then extend one more time, okay? And now this length along here, remember, it's not gonna be a perfect 180 degrees. It should be 75, better be. I'm gonna be upset if it's not. To my endpoint, endpoint, not the, right there. There we go. And if I go out 79, I must be on a little bit offset thing here. Am I through the center? 79. I'll have to look. Oops, there's a. I don't know if I got my endpoint here. I think I did. There must be, I must have grabbed something a little bit off. It should be exactly 75 because it's going to go through the center here and on the other side, which is going to be the length of my L3, and then my 25 is in line with this. So so I apologize. It's super close, 4 millimeters. So it's not terribly off, but I'd have to look here more closely to see exactly where. Is it on the center here? Looks like it is. But that's how you would lay this one out. Okay. So again, is it not? It's going to bother me. I'll kind of figure it out after we go here, but you would arbitrarily pick values. And again, starting with your crank being 1/3 or your L3 being 3 times whatever you choose your crank to be. And then that distance has to be less than whatever your stroke is. All right. So, so that is one approach. Now, the thing about these types of problems is that they are not going to be you're not going to have answers definitively because everybody's going to come up with potentially a very different offset distance. Okay. And that offset distance then, or whatever you choose your L2s and your L3s to be, then are going to, be unique to your design. But you have to make sure that you lay it out and add at least the dimensions that we see here, with the appropriate labels. Okay. So now, since I chose 75 for my L3, whoopsie, I'm going to go underneath here. Then I can go back to my problem underneath, and my L1, well, I'll actually put it down here. L1 is equal to 10 millimeters. Okay. L2 was equal to 25 millimeters, and L3 is equal to, we did 75 millimeters. Okay. So those are there. Now, additionally, we do need to determine what are the times of the outward stroke and the inward stroke. All right. So for part number 3 here, we need to determine what is T1 and also what is T2. Okay. Now we have 2 equations for T1 and T2. We have the change in time or the total cycle. So this is your cycle time. It's going to be equal to T1 plus T2. And the other equation we have is Q, our time ratio, is going to be equal to the time of the slower divided by the time of the quick return. So if that's the case, then our T1 is going to be the outbound stroke and our T2 is going to be the inbound stroke. All right. Now, for each of these, we know what the value is for the cycle because that was given, and we know what the value for the Q is. So we could rewrite this equation down here to say 3.4 seconds is equal to T1 plus T2. And over here, we can say 1.37 is equal to T1 divided by T2. All right. Now, it didn't really help us much, but we have 2 equations with the same 2 unknowns. Now, I didn't have you guys for earlier classes, but I'm hoping that sounds familiar. Right? So we have the ability with the algebra to solve these. So I'm going to show you the method that I use. All right. You do have to go through this process and solve these. So I want to determine of that 3.4 seconds, how much of it is the T1 and how much of it is the T2. Okay. So all I'm going to do is I am going to take one of my equations and solve for it in terms of the other variable. And I'm going to start over here. I'm going to call this my equation number 1 and my equation number 2. So I'm going to solve equation number 1 for T1. So if I take T2 and I multiply this up, I can say T1 is equal to 1.37 times T2, right? And then once I have that, I can take my T1, this part right here, and I can substitute it up into the other equation, right? Equation number 2. So I can say 3.4 seconds is going to be equal to, instead of showing T1, I'm going to say 1.37 T2 plus T2. T2. Now, when I have a T2, there's an imaginary 1 out front here, right? Okay, so if I want to add these 2 together, I can say 3.4 seconds is equal to 2.37 T2, right? Make sense? Are you guys confused at what I'm doing? Because this is 1.37, right, from over here. And then there's an imaginary 1 in front of here, T2. A T2 by itself, one variable is like one of those, the whole number 1. So we take 1 plus 1.37. I know, sometimes if you haven't thought about that a while, it's easy to forget. Yep. So now T2 is my only unknown variable, right? So I'm going to divide both sides by 2.37. And I'll get 3.4 divided by 2.37. And my T2 is going to equal 1.435 seconds, right? Now I'm not done. I got to find out what T1 is, but notice that I have this up here. So I can substitute this back up there. Okay. So that means that my T1 is going to be equal to 1.37 times 1.435 seconds. Okay. T1, 1.9367 seconds. Now, if I look at my numbers, T1 is supposed to be the larger of the two, right? Okay, because T1 is on the top here. It's the slower cycle. And in fact, it is 1.93 compared to 1.435. Okay. So you have to do this. It doesn't ask you to do this. And that's why I'm telling you guys, I want you to figure out using the math here, what is the slower cycle, T1, and what is T2. All right. So make sure that you do that. I'll add that as a note in the problem assignment. Okay. So all of your lengths, your crank, angular velocity, and then what are the T1 and T2 associated with the quick return. You don't have to do it on the Q is equal to 1 or the symmetrical motion ones, because they're just half of whatever that total cycle is. Okay. But when they're not, you have to figure out what is T1 and T2. Okay. So this is going to mimic then your problem. I forget if I assigned you 14 or 16, one of the two. I forget. We'll look in a little bit. All right. And you know what I'm going to do? I think that's enough for today. I think those two problems, let's look at your homework. And then what we'll do is we'll finish up with the crank rocker the next time that we're together. I think that would actually, it's a good breaking point, because otherwise I think it's kind of a lot. All right. Because I want you to get this process down first. It is the easier of the two types. And then we can build on this on Wednesday when we're together. No sense on having to rush it because we've got plenty of time. Okay. So let's take a look at those first couple homework problems in assignment number 7, kind of line those up. So, the ones that I want you to do, the 2 slider cranks. So number 12, as we identified earlier, that's going to be a symmetrical. So Q is equal to 1. And number 16, so the one right after 15, is going to be an offset. Okay. Slider crank mechanism. So you'd be able to do the first 4 numbers, 5-2 and 5-4 mimic the example that we did earlier. Okay. And so if we go underneath and we look, this says we want to determine, these are the time ratio calculations for those problems. We want to determine using the stroke value T1 and T2 on the return cycle, determine the time ratio, the imbalance angle, and the speed at which the mechanism should be driven. So we're looking for Q is equal to, beta is equal to, and our W of our crank. Those are the 3. And what was the number I said? So 5-2 is going to be your homework problem. 5-2. Then you're going to do something similar. What was the other one? Did I say 5-4? Okay. 5-4. This time you're given W and beta, and you want to determine what is your Q, and then the time to complete the outward and return cycles. So what is my T1 and what is my T2? Okay. And those are again, similar to that example problem that we did earlier in the chapter. Okay. So I think that's a great place to stop. So we will meet on Thursday to go over the process of a crank. I'm sorry, Wednesday, the next time that we normally meet, to go over the crank rocker mechanism. Because again, there's a little bit more geometry there, and this will get us started. And we'll just finish up because, like I said, we don't have to hurry through this. Okay, so I'm gonna ask, are there any questions from what we covered today so far?
Hey Kelly, what did you get for T1 for that 515?
515, I got 1.9367. So if I go, whoopsie, let me share.
Okay, because I have like 1.965.
1.965. I'll show you what I've got, because I held my decimals in my calculator. So if you rounded, so my T2 was 1.435. And there might have been one or two extra decimals, and then I multiplied that by 1.37 and got that number. And again, I held the decimal places. So it sounds like you're on the right track. Okay.
It's just like a straight multiplication, correct?
Mm-hmm. Yep. Yeah, because this would have been, we calculated 4, and then we substituted it in right here, multiplied it by 1.37, which was the Q. Okay, this was Q. This was T2.
Yep.
And then that number there.
I have the same T2,
Mm-hmm.
but then going from like doing that last step, I done it both ways, truncating it and also holding it, and I get roughly the same answer.
So if I take 4 decimal places, it's actually 4.346. I held that in my calculator. And if I multiply by, oh yeah, I get the same thing as you. Dang it. Okay. Yeah. Maybe I wonder if 654. Maybe I wrote it down wrong. I must have. Sorry about that. Thank you.
That's the correct.
Yeah, that's right.
That's what I'm getting now. Yeah.
Okay, just double checking.
Yeah, no, I'm glad you did. Any other questions? Corrections for me? All right, so we'll plan on finishing up. There's really just that one slide, one example that we'll go over the next time we're together. If you want to go ahead and attempt it based on what the rules are there and you feel comfortable, go right ahead. All right, I'm not want to hold you back, but that'll be my plan to go over that last example the next time we're together. Okay. All right, if there aren't any other questions, then I'm going to stop sharing and I'll stop recording. Where's my recording button? There it is.